Hi, teacher. Let's talk about our papers. Our paper is about extending battery life for Wi-Fi-based IoT device. First, let me introduce ourselves. Our group name is HLP. Our group member Yihao Huang is from ECE, Chao Weidos from ECE, Hua Wenpeng from CS. The paper main topic is to study, analyze, and increase the power efficiency of fully standard compliant low-power Wi-Fi IoT client. First, I will start with one key concept, PSM. PSM is named Power Safe Mechanism. PSM is the major IEEE 802.11 standard mechanism that enable low power operation in client device. Such mechanism work primarily by allowing coordination between the access point and the IoT client to power down the client when not in use while the AP buffer incoming frames, making Wi-Fi a viable candidate for low power IoT. Since PSM is part of the Wi-Fi endless certification, commercial Wi-Fi capable IoT devices often use PSM to converse power. They have been worked on studying the effect of PSM on power consumption throughout packet loss and latency, all at a high level. However, there's a lack of work that use extensive experiment analysis of a real-world device to analyze the key component of power consumption in detail. So this paper conduct extensive experiment with a state-of-the-art Wi-Fi enabled IoT model which relies on the provision in the IEEE 802.11 standard for power saving, analyze the experimental observation, and identify the component that constitute power consumption to present several key insights. Besides, we show that without PSN, even for a scenario without any data traffic, the battery life of the IoT model is as poor as 2 days, and that with PSN, the battery life is about 6 months. When a scenario with thin upstream data traffic is considered, the battery life drop down to 2 months. So you can see the picture here. Uh, you can see the picture is which the the model is configured in PSM is switched to the LPTS state between beacon reception and consuming an average current of 0.67. For comparison, this in the activity state, the model consumes an average current of 1666 when receiving beacon without any transmission in the activity state. So this is why the battery life is very long in the PSM state and very short in the activity state. And this paper designed and enhanced the NS3 simulation framework with a detailed and the generic power consumption model taking into account implication of sparse traffic and the PSM signaling to estimate power consumption considering specific network characteristic. So you can see the system here. There are three stationary node, IoT client node, Wi-Fi AP, and the TCP receiver, which model they are named six respectively. And in addition, this paper proposed five standard compliant strategy for low power operation that mitigate the impact of sparse upstream data traffic and calibrate the power consumption model to a simple link CC3235SF for simulating these strategies. In all five power-saving optimization stages, the clients remain in the sleep state between beacon reception and the advance of uplink TCP traffic. And the table shows the difference between the five optimization, like the power safe profile for URTCP traffic, power state waiting for TCP ACK, and the RTT efficiency, like that. Then with the developed simulation framework, we perform detailed analysis on the implication of specific network characteristics on power consumption. In doing so, we establish several practices bound on power consumption for common IoT traffic scenario like the periodic uplink reports over the transmission control protocol. So this paper designed a power consumption model like this to achieve realized power consumption assessment for the sparse IoT traffic scenario. The IoT traffic power consumption model is developed as a wrap scripting on top of the NS3 simulator and the process. Based on the NS3 event, the workflow of the IoT traffic power consumption model and the simulation platform is shown in this picture like that. And finally, based on the insight from the analysis, we decide a cross-layer power saving optimization algorithm operating within IEEE 802.11 standard by intelligently timing uplink TCP transmission. So this algorithm is like that. There's an algorithm is to optimize sparse TCP uplink transmission. So the process is like that. And with simulation, we show the efficiency of the development optimization in reducing power consumption. So we can see the result here. And we observe the general trend that with higher RTT, the power saving percentage decrease, and demonstrating the higher effectiveness of the algorithm for smaller RTT values. And that's all. So let's go to the next part.
I'm Huawen Peng, and I will now present the strengths of this paper. First of all, this paper is well organized and well structured, strictly follows the ACM format. We can see the screen on the right side of the screen. It's a paper. It's a structure of paper. It's very clear, right? Uh, and its content is progressive from the title. The introduction and abstract introduce the topic, the contributions, and the remaining content duration of the paper, giving us a preliminary understanding of the paper, and a large number of subtitles, body text are very clear at a glance and help us to read the article quickly. In addition, the conclusion is very concise rather than rehashing what has been done before. The second advantage is that this paper provides a lot of background knowledge to help us understand some of the terminology, such as these two core concepts in this paper, IEEE 802.11 power saving mechanism, and a kind of IoT traffic scenarios called uplink sparse traffic. IEEE 802.11 is a kind of standard mechanism that simply turns off power to the client when the client is not in use. And uplink sparse traffic is a prominent IoT use case which will occur when measuring temperature, humidity, smoke, etc. And some related studies and the reasons for choosing these elements for experiments are also mentioned in the paper. The third advantage is its simulation design. In order to analyze network conditions, device behavior, and other external factors, Network Simulator 3, or NS3 for short, is prepared to be used to perform simulations by configuring its parameters. However, NS3 has some limitations, such as absence of transitional power states, limited choice of system power states, traffic content awareness. To eliminate these limitations, the authors designed another power consumption model, which includes network identification. identification, state duration correction, power profile application, state transition addition, and current value assignment. And finally, we can get the relationship between current and time. The last point I appreciate is the author's analysis of the whole experiment. In addition to comparing the ideal experimental state with the simulated power consumption model, they also proposed 5 energy-saving optimization strategies. Power save model, it's called PSM, and long-term sleep PSM, dynamic PSM, low power dynamic PSM, and low power 2 dynamic PSI. To further identify the power consumption and RTT, round trip time, and time to next beacon, and the performance of the proposed optimization algorithm is compared to with the average case for a set of parameters, and in the end the performance is evaluated. And that's it.
Okay, I will talk about the weakness of this paper. The first weakness is there are some minor grammatical error and figures error. For example, it should be in the case of PSM, but not in case of PSM. And similarly, here, this one should be the mismatch instead of mismatch. And these words in the section 6, this word should be evaluating, but not evaluate, because there is a with here. Okay. And there are some figures that should be modified. And though the figure 5 is very good and its structures is clearly, but figure 5 should be rearranged because the alignments of the text in figure 5 make it difficult to read. And the legend of figure 12 is missing the units and names, which would make the readers feel confused. And there is not any error bars in the figure of this paper. The weakness number 2 is the reason for using the averaging time to next beacon is not specified, because the paper has mentioned the TCP transmission are expected to happen at any time to next beacon. And the paper only briefly states that this reflects the reality case. So we think the author should have detailed the reasons for using this method. or the author should count the time to next beacon for the assumed scenarios, which is the paper mentioned in the section 2.2. The lean traffic generates uplink sparse traffic, which is either periodic or triggered. And then the paper could the author could design the value of the time to next beacon based on the statistics, but not just use the averaging time to next beacon. Okay, the weakness 3 is the proposed optimization algorithm has some limitations. Firstly, the algorithm is high performance only when the RTT, the round trip time, is low. So as we can see in the figures, I showed. So as we can see that as the RTT is increasing, the percentage of the power saving is decreasing. So this is one of the limitation. And the other is the performance of the algorithm decreases when the TCP segments are transmitted earlier than the optimal. The paper has give a parameter which is epsilon to determine the RTT epsilon. The RTT epsilon is to determine the time to transmit the TCP segments at the probability 1 minus epsilon of transmitting at the time instance later than the optimal times instance, that results in the IoT module waiting an additional time to beacons for the TCP acknowledgements. So as the epsilon decreased, TCP segments are transmitted earlier than optimal. So the performance of the algorithm just decreases in the meanwhile. So the conclusion of this paper is this paper focuses on the low power operation of Wi-Fi enabled IoT clients device for the sparse uplink traffic scenarios, as I just mentioned before. And this paper has also presented extensive experimental results with the state-of-the-art IoT module. And it also analyzed 5 strategies through simulations and presents a cross-layer algorithm to optimize power consumption at IoT clients' devices. The future work of this paper is they will calibrate the power consumption model to other IoT module and analyzing the effectiveness of the proposed power saving optimization algorithm or multi-user scenarios. And they will also study the sensitivity of the proposed optimization algorithm to mismatch between the modeled RTT which means round trip times, distribution parameters, and network RTT conditions. Thank you.